So we know that the MOS behavior is completely different from a BJT counterpart. So first, let us begin with our discussion of a long channel MOS transistor saturation region current equation. Okay. So now the reason why we are concerned about the saturation current equation is that it, generally the saturation region is the most preferred mode of operation for analog circuit design when it comes to using a MOS transistor for an analog design. Okay, that is the reason why we just have this particular slide. Okay, for a transistor to be in the saturation zone, there are a few conditions that we have to satisfy. The very first thing is that the value of VGS supposed to be greater than the value of VT. So this is the first condition, and the second condition is that the value of VDS for an NMOS. Okay, so this is all with respect to the NMOS transistor is what I'm trying to write down here. Okay, the value of this VDS can be either greater than or equal to VGS minus VT. Now, in general, this VGS minus VT term can also be rewritten as VOV or the overdrive voltage. Okay, so we generally want this condition to be satisfied. Clear? And the current equation in the saturation region can be written as ID that is equal to half Kn dash W by L VGS minus VT the whole square or VOV square. Okay, so now, this is the model that we always use whenever we study those analog circuit designs in our courses, right? So now let us see the actual behavior of the circuit. I've just written down the square law relation that is towards the left side, and also I've equally represented the corresponding current components towards the right side. Okay, and what is important is that we know that the current ID is proportional to the VOE square. Okay, so based on this, when I try to plot the graph, okay, you would see that there is a kind of square law that is being used with a black dotted line. Okay, whereas I have used two different channel lengths and widths for plotting the same current graph over here. Okay, but when we look carefully here, what happens here is that you could see that the current graph of my large channel, okay, this is 20U by 2U, is nothing but it's a quite large transistor, and that could actually somewhat getting coincident with our square law model. Okay, but whereas when we take this shorter form, okay, when I'm going for a channel length that is equal to 200 nanometer, you could see that obviously there is a huge amount of deviation from the graph that has been predicted by the square law relation. Okay, and also we know that the transconductance is nothing but it is the derivative of the output current with respect to the control input voltage, which is in this case a VGS. So that when we do and when we try to plot, you could see that there is a tremendous difference between the square law model and either it is a large channel or even a shorter channel. You could see that there is a huge difference between these two laws. Okay, I hope that it makes sense. The GM value that we have predicted through the square law model is actually getting far away from what is actually happening through the circuit. Okay, when we try to plot them in the real device. Okay, so now why there exists a significant deviation? That would be the question that would be creeping right now, right? So to answer this question, we have to look at some of the second order effects which causes this significant deviation, okay, from what is being predicted through the square law. The very first thing that I just want to emphasize here is that it's a kind of graph that has been plotted on a logarithmic scale, okay, of the output current with respect to the value of VGS. Now, clearly you could see that even if I consider the value of VT, the threshold voltage, is considered to be roughly around 0.5 volt, you could see that still there exists a kind of current component when the value of VG is less than the value of VT. Okay, so even throughout this entire segment, we could see that there is a current. Okay, but what we predicted through the square law is that whenever the value of VGS falls below the value of VT, we said that the current ID is generally considered to be equal to 0. But whereas here, it reflects the fact that the term or the assumption that we had earlier is no more valid. Okay, and let us look for the second characteristic graph. So this is again, we call this as a kind of drain-induced barrier lowering, which talks about the variation of the threshold voltage with respect to the value of VDS. Okay, so generally, what we assume whenever we study our basic theory about the MOSFET is that the threshold voltage is always assumed to be a constant. Okay, but the assumption actually fails when we actually try to plot the graph between the threshold voltage and the VDS. Okay, so maybe I'll just share you a link regarding this drain induced barrier lowering. The next one is the most important parameter. So again, we talk about short channel effects, and under the short channel effects, I have to talk about what is known as the velocity saturation effect. Okay, now again, this velocity saturation effect is basically happens because of the VDS. Okay, and even this drain induced barrier lowering effect is basically happening because of the value of the VDS. Okay, so I'm just trying to convey the causes because of which these things are happening. Okay, so let us talk about this velocity saturation effect. Okay, basically the channel gets created. So let me consider this as my oxide region. Okay, and this is my metal region, and this is going to be considered as a kind of p-type material. So when I have the value of VGS that is greater than the value of VT, we know that it creates an inversion layer underneath this particular interface between the oxide and the substrate. Okay, so let me represent that inversion layer with some sort of negative charges getting accumulated over here. Okay, so this represents basically the channel inversion. Okay, or a kind of inversion that we call it as stronger inversion. Okay, so I'm going to convey this particular terminology, which we call this as a strong inversion, and we also talk about different other type of inversion that happens. Okay, yeah. So basically, in order to have a current conduction between the source and the drain, okay, we have to have a potential difference between the source and the drain. Okay, and when we have this, then we end up having some sort of current flow from the source terminal towards the drain terminal. Okay, so we end up having this drain current flowing from a higher potential towards the lower potential through this stronger inversion region. And this strong inversion region happens whenever we have the value of VGS that is greater than the value of VT. Okay, whenever we deal with shorter channels, one of the most important secondary effect that plays a major role is this velocity saturation effect. Okay, so let me try to spend some time in order to talk about this. What do we mean by velocity saturation effect? Okay, now a velocity saturation effect can be related to the drift velocity and the electric field. So let me write this as a V, which talks about the drift velocity towards the y-axis. Okay, based on the basic physics, we know that as we increase the electric field, what happens is that the velocity of your carriers become higher. Okay, so normally this is what has been predicted, that is the drift velocity is generally proportional to the electric field. So higher the electric field that I have, the velocity of the carriers will also rise up. Okay, now because of this relation, we have derived the current equation model, which is ID. Okay, and this entire formulation is being done based on the basic principle that the electric field and the velocity of the carriers actually move in the same direction. Okay, the electric field is basically defined. Okay, I'm trying to convey this electric field is a field that exists between the source and the drain. Okay, so whenever we have a potential difference between the source, so between the drain and the source terminal, then it creates some sort of electric field between these two nodes. Okay, and because of which the carriers are being moving from one terminal to the other terminal with a particular velocity, and we call that particular velocity as a drift velocity. Okay, and this entire current flow is basically being derived based on the drift velocity mechanism. Okay, but when I take a shorter channel, the electric field, which I call it as a lateral electric field, okay, just because this electric field is created by the VDS, okay, across the channel. So I could write it as VDS by the channel length, which is L. Okay. Now, once the channel length becomes small, what is happening is that even for a small value of VDS, a small potential difference between the drain and the source creates a very large electric field. Okay, and there is again the physics also plays a major role based on the quantum mechanics. The mass of the electron that creates this current, okay, also becomes large. Okay, and because of which the velocity of the carrier gets saturated, and we call this particular mechanism as a velocity saturation effect. Okay, there is a particular electric field which we call it as a critical electric field, beyond which when you try to have a larger electric field, the velocity of the carrier becomes saturated. Okay, and we call this effect as the velocity saturation effect. Okay, and this normally happens whenever the channel length that you're using is small, and due to which the current basically becomes proportional to VGS minus VT, okay? Whereas in the previous case, whenever we do not have, or whenever the electric field is less than the critical electric field, we end up having that the current ID is basically proportional to VGS minus VT the whole square, okay? Whereas here, there is no square term that sits here, okay? So that's the difference. So due to which the ID right now, whenever your transistor suffers from velocity saturation effect, the ID becomes linearly dependent on our VGS, okay? Rather than quadratic dependency, we end up having some sort of linear dependency, okay? Also, this current will also be independent of the channel length, okay? So there is a lengthy derivation that has been done, okay? I'll share the link of this where you will find that the proportionality of the length is also being removed, okay? So when I consider this current equation, we know that the current, drain current, depends on the value of L. Whereas when your transistor suffers from velocity saturation effect, the dependency of this 1 over L is not there, okay? So that is what we end up having whenever the transistor suffers from velocity saturation effect, okay? The next one is what is known as the mobility degradation, okay? And this happens because of the VGS. Now you might wonder, like, how does this VGS actually impacts the mobility of your carriers, okay? So what is happening is that when we go for lower and lower technology, the thickness of the oxide that I have here will also shrink down, okay? The thickness of this oxide, okay, maybe I will just put here, the TOX will also get shrink down, okay? And we know that the electric field that is created because of this dielectric medium can be returned as something known as the vertical electric field, okay? Because I am trying to apply a gate potential with respect to the source, right? So because of this, what is happening is that this vertical electric field can be returned as VGS by the thickness of the oxide, okay? So the moment I reduce the thickness of the oxide, the electric field across this oxide layer also increases, okay, tremendously. And because of this, all of the carriers that supposed to move in the horizontal direction, they were being attracted towards this vertical direction because I am applying a high electric field, okay? So because of this, you are forcing these electrons to rub at the interface. So you just assume that you are trying to run across a pathway, okay? So if you are in the middle, you can actually run freely, right? But whereas if you are being forced to run across the side wall, what happens is that just because of this interface, you end up hitting this surface, okay, across the oxide, and due to which the mobility of the carrier gets degraded, okay? So that is what is called as the mobility degradation. Yeah, the next important thing is that the GM, okay, actually gets saturated for higher values of VOV, okay? Now, this is something that we normally never expected, right? Because whenever we wrote this GM based on the square law, we know that this GM is proportional to the VOV. So as I raise the value of VGS beyond the value of VT, okay, what happens is that I have to have a kind of GM that keeps increasing as I move along the x-axis. But what has happened here is that you could see that the GM of the transistor are getting saturated. So one thing that we could conclude is that in the strong inversion, the square law basically gets failed, okay? So that is the final conclusion that we could see when we look at a real device, okay? So whatever the square law, whatever the current equation that we are studying in our courses actually is not true, okay? They are basically not applicable when you go for shorter channel devices. They are not applicable for nanometer technologies, okay? And due to which we end up having these many issues. And now let us see, like, how about the GM over ID term, okay? Based on the square law, I can actually derive this term, which is GM over ID, okay? Let us look, even though we know that the square law fails in the strong inversion region, okay? We'll still try to derive and see whether the prediction happens or not, okay? So again, when I've taken a current, okay, where the current is a saturation current equation, and based on this current, I am trying to create a derivative so that derivative with respect to the control input, which is the VGS, so that I end up having the GM of the circuit, okay? And when we take the ratio between this GM and the ID, we end up having 2 by VOV. Now, using this as my expression, when I try to plot, okay, here in this case, the black dotted line represents the expression quantity, okay? Now, we know that the moment the value of VGS is equal to VT, this GM over ID term supposed to shoot up to infinity. Okay, that is what this expression conveys us. Okay, but in reality, if you see, I have plotted the blue line and the magenta line. These are for different channel lengths. Okay, the blue line is for a channel length which is 2 micrometer, whereas the magenta line that I've drawn is for the channel which is of 200 nanometer. Okay, so clearly the prediction of having this GM over IC to be infinity is not valid when I'm trying to have a value of VGS that is less than the value of VT. Okay, they are actually different. Okay, also one more thing that we could see is that this GM over ID becomes a constant. The ratio of GM over ID is constant whenever we deal with a value of VGS that is less than the value of VT. We end up having, now what does it conveys? I hope that we have learned about this GM over IC was constant throughout the entire region. Okay, I guess we have seen that particular plot when we discussed about
for
the
BJT.
BJT. Yeah. Okay. So whenever it is constant, how I can predict the value of this IC to be? So this IC supposed to have an exponential relation to our VB is what it told us. Okay. So whenever the GM over IC is constant, it says that the current component in general is exponentially relies on the control input. Okay, so that is what it conveyed in our BJT. Yeah, even here we could see that this GM over ID is also constant. So this means that the current ID also somehow exponentially is related to the value of VGS. The control input here is basically a VGS. Okay, so that is what it conveys me. So in short, the ID is no more equal to 0, and it is also telling us that the ID is proportional to the e to the power of VGS term. Okay, so before we look at this current expression, let me summarize what we have learned, and then later we will just talk about how will I derive this current component in the coming slide. Okay, as I said, just because we have some sort of GM over IC for the value of VGS that is less than the value of VT, we could see that there is a constant GM over ID term over here, right? So due to this, I could say that there is a kind of current that is flowing, and that current is flowing through what is known as the weak inversion region. Okay, so I hope that you are clear. I have a non-zero current component for the value of VGS that is less than VT, and that's supposed to be some sort of inversion region, right? And we call that inversion region to be a weak inversion region along the channel. Okay, and whenever the value of this GM over ID, if it is large, okay, then we say that the current is exponentially related, or in other words, we could see that I'm in the weak inversion region. Whenever the GM over ID is constant or larger, we say that we are in the weak inversion region. Whereas whenever the GM over ID term is small, we say that we are in the stronger inversion region. Okay, so one could see that there is a kind of variation of GM over ID over the control input VGS. Okay, so due to which I can tweak this GM over ID term to define the transistor efficiency. Okay, because at different values of VGS, I have different values of transconductance efficiency. Okay, it is not the case what we have learned in a BJT. Okay, in this case, we are having some differences, and due to which I can decide like what is the efficiency I needed based on the value of VGS here. Okay, and that is the core of this GM over ID. Okay, we are having some sort of variation for the control input. Now, apart from these two different regions, that is the weak inversion and the strong inversion, we also have a third region which is called as the moderate inversion. Okay, so moderate inversion or MI. I'll talk about this. Okay, but before that, I just summarize over here. The current ID is basically can be written as an exponential relation to VGS. Okay, whereas here the current component, I can still use this square law. Okay, so if it is a square law, we know that the channel length has to be large, and due to which I could write somehow related to VGS minus or proportional to VGS minus VT the whole square. Okay, so that is what this is conveying. Okay, but we know that there are these two different current expressions. Okay, so one is telling it's supposed to be exponentially related to VGS. The other one is telling you have to be related to quadratically to the value of VGS. But there is obviously these two are two different expressions. Okay, or two different scales at which they are trying to talk. But we know that whenever we sweep this particular VGS, the GM over ID or even the current, okay, is is a kind of continuous current that I'm getting. Okay, so we cannot have two different distinct functions. Okay, so when I try to plot the value of ID with respect to VGS, you could see that there is a continuous current flow. Okay, there is nothing like an exponential current first and then suddenly it jumps to a kind of quadratic current expression. Okay, you could see that there is a continuous function between these two quantities. So now there is a kind of expression that is needed to bridge these two current components, and this bridge is created by this moderate inversion region phenomena. Okay, we know that generally in BJT, the current flow is basically defined by the diffusion current. Okay, the current is basically flows because of the diffusion mechanism. Okay, whereas in the case of the stronger inversion, where we apply the square law, we go for what is known as the drift mechanism to derive the current equation. Okay, so these are two different mechanisms through which the currents are flowing. Okay, and we are trying to bridge them. And what happens is that we know that there exists a moderate inversion region. Okay, where I'm not completely inside this drift mechanism, nor I'm not in the diffusion mechanism. Okay, so but I'm somewhere in between them, and we call that intermediate relation through which the current is flowing, still flowing, as a kind of moderate inversion zone. Okay, hope that it makes sense. So basically, what I'm trying to say is that there exist three different inversion layer when I try to tweak the value of VGS between 0 to all the way to the power supply of our circuit. Okay, and in turn, this GM over ID is also is a kind of continuous function. Okay, so it is not completely constant, nor it is not completely dependent on the value of VGS minus VT the whole square. Okay, so it is seems to be a kind of continuous behavior. Okay, and through this GM over ID, I can control certain other parameters. Like I can actually control the transconductance efficiency, and this in turn we know that it defines the speed, the noise, and the entire behavior. Okay, even the behavior of the circuit is also being defined through this GM over ID term. Okay, so one has to be careful in selecting this particular value to meet your given specification. Okay, so you could see from this GM over ID that the range of value that we have got along this y-axis ranges from a value of 1 all the way to a value of maximum of 30, or sometimes if it is a shorter channel, you end up having a value which is closer to the value of 29. Okay, or you may end up having a maximum value of 31 depending on different channel lengths that I have. Okay, so we could see that there is a particular range of values. Okay, now you might ask me, like, what is the range of GM over ID that I can say that it is equal to weaker inversion, and the range of value of GM over ID that I can say that I'm in the stronger inversion, and the range of GM over ID value for which I can say that the transistor is in moderate inversion. But to be frank, there is no hard rule. Okay, there is no hard boundaries that defines all those three different regions inside this. Okay, one thing that I can say is that whenever the GM over ID is high, okay, when the value of this GM over ID is high, then I can say that I'm in the weaker inversion. Okay, whenever the value of this GM over ID is small, then I can say I'm in the stronger inversion. Okay, and whenever I'm in between them, I could say that I'm in the moderate inversion. Okay, but still people try to define some sort of boundary to use as a kind of reference value for them. Okay, so let me roughly define this boundary, but this is not a hard rule. Okay, so whenever the range that of GM over ID falls between this 10 to 20. Okay, so anything that falls between 10 and 20, we say that the transistor is in the moderate inversion region. Okay, whereas anything that goes below the value of 10, okay, we call them as a stronger inversion, and anything that pass beyond the value of 20, we say that our transistor is in the weaker inversion. So now you might wonder, like, is my square law that I'm trying to read in today's classes can I not use it for any of the purposes? Is that is going to be an end of the usage of the square law? But the answer to this question is not true exactly. Okay, we can't say that the usage of the square law has ended. Okay, so we can still use the square law whenever we deal with a channel length that is larger. Okay, where whenever I have a channel length that is large, I can use the square law. I also have to ensure that I'm being biased in the stronger inversion. So in order to bias this transfer in the stronger inversion, then I have to have the GM over ID to be fixed to a small value. Okay, so if I fix to a small value, then this says that I'm in the stronger inversion. So if I have these two phenomena, then I can still make use of the square law. But that is not the end. Okay, one of the important reason why still we go through the square law model during our classes is that it actually makes us or helps us to understand the trends. Okay, now what do I really mean by the trends? The trends here actually means, say for example, you want to achieve a particular spec. Okay, in order to achieve a particular spec, we have to have some sort of simple model. Okay, so I need this current equation, okay, which I'm writing it as the square law model. Okay, so we know that whenever I'm trying to use the square law model, I know that the current that flows between the source and the drain is basically defined by few parameters. Namely, I need to know what is the kn dash value, and the length and the width is in our control, and the value of VGS minus VT. Okay, so these are very few set of parameters that I needed to calculate the current expression. Okay, so having the square law model actually helps us to bring out certain things. Like using this model, we know how to get the value of GM, or we know how to evaluate the value of R naught, or there are a lot of small second parameters that have been basically derived based on the simple square law model. So even though we end up having the GM that has been derived out of this square law model, still I can make use of the square law model for our understanding purpose. Okay, so say for example, you have been asked to increase the gain of a system. Okay, gain of an amplifier, and and without this simple model, I will not be knowing like what I supposed to increase. Should I need to go for increasing the value of GM or increasing the value of this honor? That is not sure, right? Because it is through this model I know that the gain can be written as the product of GM times that of R out. Okay. Now, in order to increase the gain, or in order to increase the gain, or in order to increase the GM, or in order to increase the R naught, I also have to know which particular parameter I need to vary. Okay. We know that in the case of a GM, it is actually proportional to the width, and again, it is also proportional to the VOV, or it can be also written in terms of ID as well. Okay. So this simple model shows different ways by which I can achieve this GM. Okay, but I cannot use this to actually calculate the expression. The value of this GM I cannot uh, calculate from the square law model. But what I know from this square law model is that which particular parameter I supposed to vary to achieve that high GM. Okay, so give some sort of direction to us. Okay, so okay, I have to increase the width. Okay, I should not lower the length or something like that. It conveys us. Okay, so that is what we really mean by the trends. So we want the model to be simple so that it gives a kind of direction for us, and using that direction I know what I supposed to change in order to achieve a particular spec. Okay, so but for sure I cannot use that square law model to actually calculate the sizing. Okay, so that is not valid, but it gives me the direction. So due to which, still whatever you're studying in your courses is good enough for us to understand its trend.